So we're now in chapter 12, section 3.1. No, you didn't miss anything. We were in chapter 4, but so there's a direct connection between the series solution of the wave equation that we talked about in chapter 4 and D'Alembert's solution that shows up here in chapter 12.3. So even though it seems like we're jumping around, from the point of view of the material, it's very cohesive. And actually, if you read other PDE's books, they do it in this order as well. So I think it's a good order personally. So just to remind you, now your new favorite PDE, the wave equation, which is, we've got two partial derivatives here with respect to t equal to c squared, and then there's two partial derivatives with respect to x, right? And that second partial with respect to t on the left-hand side, that's what makes it different from the heat equation. And we have our fixed boundary conditions here. Here, the physical problem is that we have a string that's being tied at, the left end at right end, and there's some tension in the string, like a guitar string conceivably, or a violin string, a very simplified version of that. And then because we have, two time derivatives, we have two initial conditions, an initial position and initial velocity. We typically distinguish between motion of a plucked string versus motion of a struck string. So the plucked string velocity is 0, and the struck string, there's some velocity and initial position. So anywho, you know that using separation of variables, our traditional separation of variables, we get this formal series solution. And then, using the orthogonality of the Fourier basis, Fourier sine basis, we can find the coefficients have these formulas using the orthogonality formula, which, by now I hope is very familiar to you. So this is all well and good, but, here, is it possible to find a closed form solution? That's really the question. Is it possible to find a solution that's not an infinite sum? If we can find a solution that's not an infinite sum, then, we don't have to worry about these convergence issues. So of course, the only reason I'm asking that question is because yes, it is possible. And so here we want to start with some very simple trigonometry. We have these two identities, which we talked about, in the review so many weeks ago. And this is why, I wanted to review those trig identities, and because we're going to use them right here now. So if you look at the series solution, the first term has a sine n pi x times a cosine n pi ct. And what you should in particular notice is, one's the x variable and one's the time variable. And we talked about the space wave and time wave. So here, using this identity, the sine A cosine B identity, I can rewrite this first product, superposition product solution part of our formal solution. I can rewrite it as a sum of sines, where inside now we have this x plus ct and x minus ct. And similarly, for the other term in the formal series solution that involves the sine n pi x, the space wave times the sine n pi ct here, use this identity over here and rewrite that second term. And here again, you should notice there's a x minus ct and an x plus ct. So now what we're going to do is rewrite our standing wave formula, for each fixed n in that series, right? If you take a sum here, if we do a sum and going from 1 to infinity, we get our formal solution. So anywho, replace the first term, replace the second term. And so now what I'm going to do is look, there's an x plus ct here, x plus ct, and there's an x minus ct here and an x minus ct. Let me combine all of those terms that are functions of x plus ct, and then let me combine all the terms that are functions of x minus ct. And so now here, I've put all these terms together that should go together. So all the x minus CTs are over here, and all the x plus CTs are over here. And so now, if we step back and take a look, you know, we notice that, well, this portion here is entirely a function of x plus CT. And this other portion over here is entirely a function of x minus CT. I went with a very kind of fall palette there. I was feeling inspired. So that's the, you know, motivation for D'Alembert's strategy. The question we now ask based on that math in the previous slide is, can we find a solution to the wave equation that has the form some function of x minus CT plus some function of x plus CT, where remember C is the speed of the signal propagation, you know, along the string, wave speed. So again, the only reason I'm asking this question is because the answer is yes, right? I just want to say no, class is over, see you on Friday. So now we introduce the so-called natural variables based on, you know, this kind of emergence of x plus CT and x minus CT as potential new ways of parametrizing the solution of the wave equation. So now we've introduced these new variables. Let y equal x plus CT, and, you know, just following the notation in the book. If you read a different book, they'll use different letters, right? Usually I've seen they'll use Greek letters like eta and zeta, something like that. But anyway, here z equals x minus CT. Or maybe our book does, I can't remember. So now we've got these two new variables. And, you know, we can always go back to the original variables. So here I solved for x and t in terms of y and z. Here, if you add the two functions, if you add y and z, the CT parts cancel, and you get, you know, y plus z equals 2x. And similarly, you can solve for y and t. Okay, and here I graphed the new variables. And so here's our old variable system. Here we've got t, which is time, greater than or equal to 0. And then we've got x, our spatial variable, which I'm allowing to be all reals. And what I did was I graphed, for example, y equal to x plus CT. For example, if you look at this y equal to 0. So here what I did was I assumed c is equal to 1, just for the sake of being able to graph it. I assumed c is equal to 1. And for this y equal to 0 case, what I'm doing is replace y by 0. So here I'm going to have a 0 in here. And also replace the c right there with a 1. So replace this c. And that was like a random choice, you know. So here, let me replace this c with 1. And so now if you solve for t, put a 1 in here. I guess I didn't need to write it in. If you solve for t, you get t equals minus x. And so that's what I've graphed basically here. We have the graph of minus x, but just the part that's, you know, above that x-axis based on our parameterization. And so for this new, you know, what we call natural variable coordinate system, these are like the natural grid lines. Like this, if you bought graphing paper for this new coordinate system, it would have these grid lines here, you know, without the x and t necessarily. It's a new kind of axis. And we can, you know, it's as good as any point in this, you know, x can be any real number, t has to be greater than or equal to 0. Any point xt in that upper half plane can be written in terms of yz coordinates. So for any point here, we can always find two lines, a y line, sorry, a z line, and a y line where it'll intersect. That wasn't a very good, where it'll intersect. So one of these will be a y line, and the other will be a z line. And then that intersection point will be the coordinate of y and z. So it's introducing this new coordinate system to now, you know, see if we view it from this different coordinate system, is it easier to solve? And so certainly we'll get some results, right? So here we have to be very careful now. I first need to translate the original wave equation, which is in terms of the x and t variable. I need to translate it into the y and z variable. So here, be very careful here with what I'm saying. So u of xt is the solution, you know, described in terms of the x and t variable. I'm looking for the same solution described in terms of the y and z solution. Now be very careful. It's a very subtle point. It would not necessarily, would be incorrect. It would not be correct for me to write u right here. And so let me switch over to the document camera for a second and show you a very cheesy example. Just, you know, because I think it's important that we make sure we know what's going on to some extent here in terms of the notation. Why did I write v instead of u? And in some cases, the book is a little bit, I think, you know, incorrect in the way they're writing their notation when they change their variables. So let me switch over here to the document camera. So, okay, here we go. Okay. So, you know, I wrote u of xt equals v of yz. And remember here, we have that x equals, for example, y plus z over 2, not for example, that's x equals, and t equals y minus z over 2c. I'm going to use that in a second. Okay, so here's my little example. So suppose u of xt is x plus t. Okay. So here, my point is here, if I write, well, u of xt is actually, now if I replace x, this is y plus z over 2 plus y minus z over 2 c. And then, you know, we can do more math here, which we don't need to, but I feel like I'm about to. yc plus y over 2c, right? Plus zc minus z over 2c. Oh, you're doing too much work. So here you see, this is actually x plus t in terms of the new variable. This is what I would call v of yz, because it's a new function. If I wrote u of yz instead of v of yz, well, according to the formula, u of yz, you know, here I'm just replacing x with y. So here this would just be a y. And here I'm just replacing t with z. U of yz is y plus z. That's obviously not the same as this function here, v of yz, which v of yz, this is equal to u of xt. That's true. You know, u of yz is the same of x as x plus t. We haven't changed the variables. It's not in a new variable system. This is still basically in the old variable system. So that's why when I go from xt variables to yz variables, I rename the function. I call it v of yz, because the actual formula is not the same. Right here, u of yz is just using the same formula, but with different squiggles. However, in the new coordinates, the formulas aren't just the same. So yeah, I'll let you think about that. And so that's what's going on here with my notation. That's why I did this shenanigans right here. Okay, so now here's what we have to do. I need to find the second partial of u with respect to x in terms of y and z. Okay, so what we're going to do is we're going to do a chain rule. And here, let me just remind you, it helps to have the tree. So just, let me just remind you of what the tree looks like. Okay, so here, let me make some space. So here, remember we have a function v, which is a function of variables y and z. Now look here, y and z are functions of x and t. So y here, this is a function of x and t. And z here, this is a function of x and t. So, you know, if I now say, replace u with v, and now I want to find, you know, to find the second partial with respect to x, I have to first find the first partial. So I would do partial of v with respect to x, and then, you know, we'd do our chain rule and follow the difference. So here I'd have to do partial v, partial y, then partial y, partial x. And then here I have to do partial v, partial z, partial x. You know, and here we can take all of those partials because we know the formulas. And the same thing will happen for when we do partial v, partial t, okay, which is on the next slide. Okay, so here we go. So first I need to find partial u, partial x before I can find the second partial. Now I'm replacing u with, you know, what u looks like as a function of v and z. It's still the same function, but it's a different formula because it's in a different variable system. And so now I'm using chain rule. So here, for v is a function of y and z, right? So I do partial v, partial y, partial x, plus partial v, partial z, and then partial z, partial x. And that's just our usual chain rule shenanigans. You know, it helps to have that variable tree I just drew to kind of help your intuition. And so now we can calculate partial y, partial x, because I know y equals x plus ct. So I know partial y, partial x will equal 1. And we can also calculate partial z, partial x, and we know z equals x minus ct. Partial z, partial x also equals 1. So here we have partial u, partial x in terms of the y and z variable looks like, you know, partial v, partial y plus partial v, partial z. And so the left-hand side and the right-hand side, they're equal, just in two different variable systems. And, you know, we've discovered a more general rule here. And this is also why we did so much chain rule on that first homework. So here we've discovered a more general rule that in general now, I know if I have a function that's a function of the y and z variable, and I want to find its x derivative, then the formula of that function's x derivative will be f partial y plus f partial z. You know, if we're using the parameterizations here that we're using for y and x, that's always going to be true. There's nothing special here about the actual function v. We just use chain rule. So go slow. Let's just go really slow. So now what we want to do is find the second partial. So what I want to do is I want to take the x partial of partial u partial x, but I want to use this y and z version of it. So I'm going to replace this. Now here's the really important part to remember. V partial y is itself a function of y and z. And V partial z is itself a function of y and z. So what? So when I try to find the x derivative of V partial y, I'll use this formula. The only difference is I replace f with V partial y. When I try to find the x derivative of V partial x, I use this formula. Only difference, I replace f with V partial x, or V partial z, excuse me. That y is screwing me up. I keep going y and x. So I'm going to do that on the next slide, okay? But the main thing now is to remember this more generic rule for finding the x derivative of a function of y and z based on chain rule. So now one more derivative, one more x derivative to find that second partial. Here, partial u partial x, let's replace it with its, YZ version. Now, here's where we have to, I'm going to take the x partial of Vy plus the x partial of Vz. So for the x partial of Vy, the rule is if you have a function of y and z, the x partial of that is take the y partial of it. So here I have Vy, and then you take the y partial of it, plus take the z partial of it. So I have Vy, and then I took the z partial. Plus, so this plus right here is right here. Now, we're going to take the x partial of V sub z. Here's the important part. V partial z is itself a function of y and z. And we have a generic rule for finding the x partial of a function of y and z. You take that function and find its y partial, and then add it to its z partial. And so now, I can write it in Leibniz notation, and we can combine the mixed partials here, V partial YZ and V partial ZY. We can, assuming continuity, you can change the order of those and combine them. And so take a step back and think about what we've done here. We've found one side of our wave equation in terms of the y and z variable. Let's do all of that over again, except this time we take the derivative of v with respect to the t variable. Okay, folks, I'm going to do it again, and I hope you find this boring. Let's write down the variable tree. Okay, so here you got the old v, and then v itself is a function of y and z. I don't know if I should put that in one of these slides. And then y is a function of x and t, and z is a function also of x and t. All right, let's think this through. If I now want to, we're going to want to find partial u, partial t, but then we replace the u with v. So for partial v, partial t, I'm going to first do partial v, partial y, then partial y, partial t, plus partial v, partial z, partial t. And the partial y, partial t, and partial z, partial t we can find because we know y equals x plus ct and z equals x minus ct. Those are the new natural variables we introduced. All right, folks, let's do some chain rule. So here it is. I'm doing the t derivative of, something that's a function of y and z. So chain rule kicks in. Partial v, partial y, that's, that's a natural variable for v. So we take that derivative, partial v, partial y, partial t, plus, as you know, chain rule now, the other variable, the natural variable for v, partial z, which itself is a function of t, so times partial z, partial t. And now remember here that y is x plus ct. Let me write that down. Y is x plus ct. And z is x minus ct. Alrighty. So now we can find the partials, right? So here, partial y, partial t. So this term right here, whoops, let me do a different color. Partial y, partial t, this term right here, take the derivative of this with respect to t, you get c. And here, partial z, partial t, take the derivative of x minus ct, both sides with respect to t, you get minus c here. And now c is a common term, so let me factor out the c. And here I'll use this alternate notation. So now what we've successfully done is we found the partial of u with respect to t in terms of this new representation, in terms of the new y and z variable. We've actually learned a more generic fact than that. There's nothing special about v. We've learned a more general rule. So the more general rule we've learned is that for any function that's a function of the letters y and z, if you want to find its t derivative, then you do c times, take that function, take its y partial, minus the z partial of that function. So here, to kind of connect all the dots now, remember that the, v partial y is a function of y and z. So if I want to find the t derivative of v partial y, this rule applies, where we're replacing f here with the v partial y. And the same thing for v partial z. V partial z is itself a function of y and z. If I want the t derivative of v partial z, I just replace f here in this formula with v partial z. And so that's what we're going to do here. I now need the second partial of u with respect to t, which is, the partial of t of partial u partial t. Now replace partial u partial t with, its version in terms of y and z, which we found using chain rule in the previous equation. These two are the same. So now, very slowly here, we're just going to use this formula repeatedly. So let's keep track of everything. The first thing we'll do is take this c right here, which is a constant, and pull it out completely. Okay, and now for v partial y, we're going to take the t derivative. So when you do that, you need to put a C. So if you look at this formula here, I need to get a C. And so I have that C right here. And then it says you do the y partial of the function. So here I have y partial of v partial y. And then it says you have to do the z partial of the subtract the z partial of the function. So there we have, this entire term here is the partial of v sub y with respect to t. And then we have this minus sign right here. There's a minus sign, which is going to show up right here. And now I need to do the t derivative of this function v partial z right here. And again, we're using the same formula. I need to get a c and then do, y partial of the function minus the z partial of the function. And so that's what you see here. So here I have the y partial of the function. Oh, here's the c. Here's the c. Then the y partial of the function minus the z partial of the function. So this entire term is the t partial of v partial z. It's not difficult. It's a little tedious. It's a lot of Calc 3 chain rules stuff, and you just want to, go through it slowly and draw the variable tree. There's not going to be any chain rule on the homework, anything. Don't worry. We're done with that. So then, we write it in Leibniz notation. And so at the end of the day, we have the left-hand side of our wave equation. So I want to set this equal to c squared times this term up here. But we have to multiply this because it's the second partial of u with respect to t is equal to c squared, the second partial of u with respect to x. So I have to multiply this by c squared. And you can see what will happen. There's a c squared on the other side. So we'll be able to simplify this equation a lot when we set them equal to each other. So here we go. The final steps here of getting to this heat equation in these new variables, which we'll use a slightly different approach to solve. We won't use separation of variables, not the traditional separation of variables. So here my second partial of u with respect to t, as we showed on the previous slide, is this mess. And c squared. So now I'm multiplying by c squared. Okay, c squared times the second partial of u with respect to x is c squared times all of this mess that we showed on like 2 slides back. And so now we're setting this stuff equal to this stuff for our wave equation. And you see common terms cancel. So here, the second partial with respect to y cancels. The second partial with respect to z cancels. All we're left with is this center term here and the c squared, which we haven't canceled, and I'll say why we haven't canceled. We can mathematically, but we're not going to, so hold on. I'll say why we haven't done that. And so here, that's what we've brought down here. So you see they're in the same variables. So now what we do is we take one of them. So I'm going to take this one, move it to the other side. This negative becomes a positive, and we get, 2 of them plus 2 of them, you get 4 of them. Now, if we want, we can divide by the 4, but we're going to keep the c squared term. And so now the question is why? And this is the part where we have to remember, this is the subtle difference here. It's because we're doing applied math. The c squared term has all the information about the string tension, the density of the material. So c squared is really important in terms of the physical modeling. it has information, physical information about the string that we don't want to lose. That's the whole reason, that's, you know, why we're doing applied math here. That's why we've created this PDE based on physics that's taking into account these, you know, real world concepts. So here I could mathematically divide by the c squared, but that would be a huge applied math blunder. The c squared has valuable information about our system, about the string. So yeah, if dividing by 4, if you divide both sides by 4, you get, this is the heat equation in terms of these so-called natural variables, y and z, where y is x plus ct and z is x minus ct. And so now, you know, we want to see, okay, we've got a new PDE that's relatively simple, actually, if you look at it. And so now, if we can solve this PDE for v, then in theory, we'll have found some type of solution of the heat equation. So let me just pause for 1 second, because we're about to now start that second phase. So up to here now is we've derived the heat equation in terms of these new variables y and z, and that's right here. Now I'm going to start to try and characterize what the solution looks like. And this is where we'll see what we call this standing wave phenomenon occur. This sum of standing waves, this D'Alembert's standing wave phenomenon, maybe is how I should say it. Okay, so we start with this PDE right here. We can ignore the c squared for now. And what I'm going to do, just to make this a little bit easier to read, because we're going to break this down, I'm going to write the partial v partial z part. I'm just going to write that as v sub z. So that's what I've got right here. So that equation is identical. Okay, so these two equations are the same. I just want you to take a second and look at the notation. In both equations, we're taking the y partial of partial v partial z. Okay, so that's what we have in both equations. We're taking the y partial of partial v partial z. Okay, so now let's start with this equation here. This equation says if I take the y derivative of partial v partial z, I get 0. So that says partial v partial z is a constant in terms of t. There's no t variables in v in the formula, so for v partial z. If there was a t there, when you take the t, if you take the y derivative, I don't know where I got t, son of a, sorry, got so excited. We take the y derivative of, you know, that function, never mind that's v partial z, just think of it as a function, and you get 0, well, that means it doesn't have the y variable in its formula. It's a constant with respect to y. So, but that constant could be a function of x though, you know, so here we say v of z is a constant with respect to y, but could be a function of x. So in terms of notation, I'm going to write partial v partial z here. I'm going to write this as a function of z. I'm going to write it as a function of z. And here I wrote it as being equal to f prime of z. Why didn't I just write f of z? The f prime is for notational convenience. You'll see later, it makes the answer look nice. But it wouldn't be wrong to call this f of z, you know, but I'm just doing the traditional derivation here. So certainly you could just call it any function of z that you want. But here, for notational convenience, I've slipped in a prime here, okay? So if that seems weird to you, then you're absolutely right. But here, you'll see later on, it'll give us a nice answer. It'll just look nice. So basically, my assumption now is partial v partial z is some type of function of z, which I'm calling f prime of z. And we integrate this with respect to z, because I have a, you know, a z derivative. So integrate, and so now we get, oh, here's a nice notation, you know, here now I get v of yz equals f of z plus a constant. And I say with respect to z, what do I mean? All I'm saying is here, this doesn't have necessarily any z variables in it. It's just a constant. It could have y variables though. So here we did an integral dz, keep that in mind here. On both sides, when you integrate with respect to, like, for example, dx, we get a plus c, where that constant, doesn't have the x variable in it. That's what I mean by it's a constant. So here we have a constant that doesn't have a z variable in it, could be a function of y. So now we have an expression for y, for v, excuse me. So let's plug that into our heat equation. So remember, we had this heat equation. So let's plug this in and use a similar type of analysis. So here, I reverse the order of the PDE. So look here, we had partial y, partial z, and now I've changed the order. And I'm going to do a similar type of analysis. I'm going to say, if the derivative of this function, never mind that it's partial v, partial y, just think of it as a function. If the derivative of this function in here with respect to z is 0, then it must not be a function of z. It must be essentially a constant here, in terms of z, but it could be a function of y though. There's nothing precluding it from being a function of y. So I'm going to now assume partial v partial y is a function of y. And for notational convenience, I'm going to call it g prime of y. And now to solve for v, I'm going to now integrate, that's a terrible integral symbol. I'm going to integrate both sides dy with respect to y. Integrate both sides dy. So on the left-hand side, when I integrate with respect to y, this term here is vyz. Integrate this with respect to y, I get g of y plus a constant. What do I mean by plus a constant? This is something that doesn't have a y variable in it. It may have a z variable in it. Okay, so now compare both of these equations. Look here, I say v of yz is some function of z plus a constant with respect to z, could be a function of y. But this other equation here says v of yz is a function of y plus some constant, i.e. constant with respect to y, could be a function of z. And so if we compare the two equations, we kind of make the conclusion that this constant here, that's a constant with respect to y, that's probably this function f of z. And this other constant here, that's a constant with respect to z, but could have a y variable in it. That's probably g of y. And so I conclude that v of fyz looks like f of z plus g of y. And f and g are functions that we don't know yet, but we can use the boundary conditions to find f and g. So if I can find f and g, and if I can go back to my x and t variable, then we've solved this equation. So here, I can go back to the x and t variable right away. We already know how to do that because we know the formula here for y and z. And so here, I can write the solution in terms of the x and t variable. And remember, in the x and t variable, the function v in the x and t variable is actually just u, the function u. V of yz was just another way of writing u of xt, it's just different variables. So here's our solution structure that is the new strategy we want to try. So this isn't separation of variables in the traditional sense, but we do have this kind of decomposition of the solution into this x minus ct term and an x plus ct term. In terms of the original variables, it is a type of separation. However, here they're being added, not multiplied. And so how do we solve the wave equation now? And I'll show you this next time, is we're going to take this expression and plug it in for u. So I'll replace u in the wave equation with this mess. And then we'll use the boundary and initial conditions to find f and g. Once we've done that, that function that you have will be a solution in theory. It'll be a type of formal solution, based on this analysis. And of course, technically we still need to verify and all that kind of stuff. But we'll get to that when we actually solve the wave equation. So just some quick definitions of the stuff we just saw, and let me just wrap it up real quick, and I'll stop here after this. This function f of x minus ct is a waveform. It's known as a waveform that moves to the right with velocity c greater than 0. So remember here, t is greater than 0 and c is greater than 0. So think about translating the graph. When you do x minus ct, that's a translation to the right. So this is a wave that moves to the right. And the other wave, traveling wave, excuse me. So these are traveling waves. The g of x plus ct, remember, think about the translations, from Calc 1, your graph translations. Remember, c and t are positive. So this would be, when you add, it's a translation to the left. And, the solution here, if we can find it, as long as all the required derivatives exist and are continuous, then that solution will be a solution. We won't have to worry about convergence. So here I just want to talk about why this is slightly better, or what are the advantages of this traveling wave solution as opposed to the formal solution, the standing wave solution that we find using separation of variables. And as I mentioned, f and g we can find using boundary conditions, and I'll talk about that next time. With the Fourier series here, we have all these convergence issues, and we require certain amount of smoothness from the initial position and initial velocity. We need certain amount of nice continuity and differentiability conditions for convergence there. And here we're not going to have that issue. Here, with this type of D'Alembert solution, if we can find it, we don't have these convergence issues. All right, everybody, that ends this. So next time I'll use this strategy of traveling waves to solve the wave equation. Thank you for your time, everybody. I'm going to stop right here.